Hi, welcome to possibly, I have to think about it, but the last video I might be making for your class this year, this semester. Have like a Kleenex handy right by you in case you cry, but we want to think about these synthesis problems. Okay, there's three of them. I know I usually put like a fairly challenging synthesis problems in the notes, but these ones fairly easy, straightforward ones, I think, I hope. So I hope you've had a chance to tackle them and maybe come up with your own answers. Really, the sort of the struggle you go through by thinking through synthesis problems, that would be more educational than watching this video alone, I think. So please take at least a few moments to think about this, but trusting that you have this first one. We want to make this, this is essentially a fatty acid. It's a long chain carboxylic acid. How would we chemically synthesize that from a malonate ester? Here we have a dimethyl malonate as the starting ester material. And remember, malonate Claisen is a really good way to make carboxylic acid, right? Starting with malonate. And you just have to swap out this second step with different alkyl halide or alkyl leaving group. And so what we need to do, and remember, one of these carbons gets decarboxylated. Maybe you could say this one gets decarboxylated. So these two carbons come from the malonate. The rest of it must be from the alkyl halide, okay, that we're gonna do use in the second step. So hopefully that makes sense to you, that strategy. So what do? We need to make an enolate. In this case, we have a methyl ester, so instead of using sodium methoxide or anything like that, we should go ahead and use sodium methoxide, which should give us cleanly enolate that looks like that. And again, it doesn't matter which oxygen you put that negative charge on, it's, there's resonance, right? And then the second step, we need to have 1, 2, 3, 4, 5, 6, 7 carbons and a leaving group. Iodide is a great leaving group, so let's just use that. 1, 2, I already forgot how many carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 carbons, and so that would give us technically that would give us this intermediate. 1, 2, 3, 4, 5, 6, 7. Yeah, and because if you treat that with an acid, aqueous acid, you can make that into turn that into a neutral diester, but we're interested in forming the carboxylic acid and decarboxylating one of these carboxyl groups. So to do that, you could sort of kill two birds with one stone, in that you could go ahead and add strong acidic aqueous solution, but at the same time heat this up to encourage the decarboxylation and get to that product. Okay, so that's the one problem there. The second one, we are forming a ketone. So I want you to immediately think about acetate ester Claisen, but where let's see, these carbons come from that, this gets decarboxylated. That's the idea. So we need to introduce this portion of the molecule as some sort of alkyl halide. And this would be great too, because this is the carbon that would have had the leaving group, and that would be an allylic leaving group. And remember from the previous chapters that allylic halides are particularly good at SN2 reaction. So this is a really nice setup. So how do we do this? Well, first of all, the study material is not, well, an ester, so we gotta contend with that. But technically, this last problem, I kind of broke the cardinal rule of starting from the target, so maybe we'll actually do that this time. So we should have had this material, maybe some sort of an ester, and that gets hydrolyzed and decarboxylated to get to this. Now, to get to that, we need to make this bond, right? So the way to do that would be having something like that. And since we're using ethyl ester, maybe for the base we'll use sodium methoxide. Ooh. And since I just drew a neutral form there, I guess that would mean that I would have done some aqueous workup. Now, that is assuming we're starting with an ethyl ester, like this ethyl acetoacetate. So we need to form that ester. One way to do that, we could make acid chloride, introduce ethanol and some base like maybe triethylamine, which in my mind is healthier than pyridine, so I tend to prefer that whenever I can, so that would complete the synthesis. This last one, let's think about this. This one is a little bit trickier, perhaps because we don't see any carbonyl functional groups in the last or the target, but we do see something that we could make from carbonyl, like these alkenes, right? Like you could dissect them right here. Now, hopefully you're already thinking of the reaction you could use to make that olefin or alkene from carbonyl, and that, of course, would be Wittig. And so if we use 2 equivalents of this methylene Wittig reagent, we should be able to make that target compound from this beta diketo compound. Okay, or you could say 1,3-diketone. And I immediately want you to be thinking about Claisen condensation of some sort when we do this. Right, so one way to do this would be maybe dissect right here. Okay, then we could envision making that from the xenolate, attacking an ester with 3 carbons in the carboxylate and acid workup. That would do it. This is just a Claisen condensation, and to make that selectively we could do LDA deprotonation. So that's one way. Just for the sake of review though, like maybe we could try to think of other ways, perhaps, like well, maybe the other ways it's not that interesting. So technically you could do this mixed or crossed Claisen, because this ketone only has enolizable protons on this carbon but not on the other carbon, so that would be selective. And remember, ketones are more ketone alpha protons are more acidic than esters, so we technically could do it like this. Right, and that would complete the synthesis as well. Okay, all right, well, that is it, folks.